So the first thing we're going to talk about in this chapter is going to be electric fields. Everything we're going to start out by talking about with electric fields can be done through a discussion of electric forces. And really what it boils down to is you can look at the interaction of two charged objects as either a single step process or a two-step process. The force way is just to say that directly there's one interaction. Nothing happens if you only have one charge. There is no force produced, but you only find the force by just plugging into Coulomb's law, finding the force directly by knowing how far apart the two charges are and what their charge is. Now, what electric field does in contrast is it breaks that problem into two different parts. The first idea is that the first charge, let's call this, if you can see my mouse here, right here, we'll call this charge 1. It doesn't have to be a particular sphere or anything, but just a charge at a certain location. And we're going to say that charge 1 is doing something that causes charge 2 to feel a force. And what it does is creates an electric field. Now you can think of that as it creating a message, as if charge 1 was shouting at the top of its lungs some sort of signal that would send out through space, that then charge 2 listened to, so to speak, picked up on, and responded to. And the way in which it responds is by feeling a force. So the force is the response to the electric field. Okay, and this is very easily confused. Forces, electric forces, and electric fields are similar concepts. They're both vectors. They both have a magnitude and a direction, but they mean drastically different things. The field is what the charge is doing, and the force is how another charge responds to that electric field or that message. I like to use as an analogy. Now, I want to make a note about this new quantity we're talking about, electric field. It's going to go by a capital E. Be careful because energy also goes by a capital E, so this is going to be one of those cases where you're going to have to see, does capital E mean electric field or energy, and guess based on the context. Another note is that you can see from my mouse, sure, that the electric field has a little vector above it. And the reason why is it is a vector quantity. If I wrote this without a vector, I would mean the magnitude of the electric field. That's the usual notation. If I leave off that little arrow, I just mean the magnitude of it. Now its units are a Newton per Coulomb. Again, Coulomb being the measure of how much charge you have and Newton being the measure of how much force. It has no special name. We just usually write it as a Newton per Coulomb. Also, when we'll talk about a different type of quantity called electric potential or voltage, you've probably all heard of a volt. You can write this in terms of a volt. We'll talk about that later, but for right now, we'll just talk about how many newtons there are for every coulomb of charge. Now, what what I want to note also is that this is not just a vector. This is something called a vector field. Now, a vector field is a vector at every point in space. Now, that means we want to draw, and to get the full amount of information, an arrow everywhere, indicating how the electric field is at every location. Now, when we do that, the convention that we have is that the base of the arrow indicates where it is that we're talking about the electric field. So if I had this picture right here and I drew this rightward arrow, I would mean the electric field at the location of the star is to the right. In other words, there's some charge out there somewhere that's creating an electric field, that's sending out this message that's saying, go to the right, okay, at that location. If you sort of sat there and listened, that's what you would hear. And of course, this hearing is analogous. You don't literally hear this with your ears. Be careful not to confuse that. But that would be the signal that would be picked up by charge. Now, you've probably seen vector fields before, and the most common way you've seen it is in a wind map. If you ever watch the weather, they'll usually at some point show you which way the wind is blowing and how strong over some region. And they usually draw a picture like this, or probably a fancier picture because this is just one I took off the web. And what this is indicating is that over here near the blue arrow, all of these arrows are going over to the right and are relatively short, so that the wind is blowing to the east and fairly slow. Over here, it's blowing to the east and south, so southeasterly roughly, but because the arrow is longer, that means that it's blowing faster. And if I drew this for the electric field, I'd be showing what is the electric field at all of these different points. Now, you can kind of guess what's going on in the spots in between here, but so it isn't really a full map of what's going on, but it's usually enough information to roughly show you what's going on over the whole map. And we'll talk about different ways you can actually show this information a little bit more clearly for electric fields in particular. But for right now, if I say the electric field caused by some object, I'm going to mean all of the arrows, all of the vectors that are at every single location, telling you what is it that that charge is saying everywhere, because it's always in some different direction and in some different magnitude at different locations. Or typically, I should really say. It's not always different. Now, the first step you're going to have to do whenever doing a problem with electric fields is figure out what I'll call what does the charge say, which is in technical terms what is the electric field that this charge is producing. And it's really straightforward. It doesn't matter about anything at all about what's around the charge. It only matters what type of charge it is to get the direction, and then the amount of charge will tell you about how large the electric field is. And the basic idea is that the electric field always points away from positive charge and it always points towards negative charge. Now, this does not mean that it's attracted to negative charge and repelled from positive charge, because that's force language. That's a discussion of how you get pushed. Rather, what it's saying is that positive charge always says go away, and negative charge always says come toward, no matter what's around it. Now, things around it will respond in different ways, either being pushed away or pulled in, depending on what type of charge they are, which is the second step. Now, but before I get to the second step, let's talk about the first step again by talking about the magnitude of this. So, in this case, we want to know not just in what direction is the electric field, or in what direction is it being told. It's always towards or away. But how loudly, how strong is this electric field? Now, the formula for it is that E sub q equals k sub e q over r squared. What does that mean? Well, note that I've left off, this is a capital E standing for an electric field. I've left off the arrow, which means I'm talking about magnitude, not the electric field overall, because I'm not specifying anything about the direction in this formula. Sub little q means the electric field that charge little q, whatever I've called little q, is creating. So it's the same charge that goes into the formula. If I have a little teeny iron ball that has some charge on it, then that charge on the ball is what I would plug in for q. And it only depends on the thing that creates the charge. So it's the charge of the thing that's making will eventually make the force. Now, K sub E is this electrostatic constant, sometimes called Coulomb's constant, the same one we looked at when we talked about charge. And R is how far away it is. Now, there was only one object to talk about in this case, so it's not the distance between two objects. It's saying, if I want to know how far, how loud, so to speak, the electric field is, say a meter away from the charge, R would be 1 meter. So R is the distance between the point you want to know what the electric field is and the location of the charge. And for this formula to be true, it will have to be talking about something called a point charge. And a point charge is a charge, break for a second. A point charge is a charge that, a point charge is a charge that has negligible size or space, meaning that it's small enough that you can treat it as a mathematical dot. It doesn't matter that if it's shaped like a gummy bear, or if it's shaped like a round ball, if it's shaped like a raisin, it doesn't matter. And anything that is relatively small in a problem, so that if you wanted to draw it, a dot would look fine, generally is going to be reasonably approximated as a point charge. It's only when you're relatively close up to an object compared to its size that does the actual dimensions of the object, the actual like length, width, and height matter. So most small objects compared to the distances between objects. So if something, say, like the size of a raisin, and you're talking about the electric field a couple inches away, that's fine to use as a point charge if it was a charged raisin. Um, but if you were talking about electric field on the very surface of the charge, you wouldn't want to use this approximation. Um, Now, so that's how you're going to find the electric field of a point charge. Now, do note that not all charges have the same formula. So if the shape is no longer negligible, like it's a very large object, and we're going to take a bunch of infinite objects, meaning that they're so big the edges are far enough away you don't care whether they exist or not. Um, for those objects, they're going to have totally different formulas for the electric field. So keep in mind that this is only for a point charge. Now, once you figured out what it is that the first charge says, so the electric field it creates, then you want to find how do these other charges respond, and they respond by feeling a force. And again, it depends on the type of charge that is being pushed or pulled. Okay, so now this is the charge that feels the force in this problem. Now, if it's a positive charge, it'll be pushed in the same direction as the electric field. If it's a negative charge, it'll be pushed in the opposite direction of the electric field. So I like to think of this as in terms of this analogy, as a mnemonic about a child, a needy child, and a sort of dutiful parent. Now, the positive charge is that dutiful parent. What it says is always, go away, go away, go away. It just wants to be left alone. Yet, if it hears the message, come here, it'll go and it'll actually go in that direction. It'll be pushed towards, it'll be pulled in towards the direction it's being told to go. Now, the negative charge in this analogy is like a needy child. The needy child always says, come here, come here, come here, come here, come here. Always says that, never says anything different. But if it's told to do something, it does exactly the opposite of what it's told. So if it is told to go here, come here, it'll run away. If it's told to go away, it'll run in. Now, hopefully this will help you remember that there are two distinct different ways in which things either create electric field or responds depending on what their charge is, and the fact that it always is the same direction depending on the charge. Now, once you know the direction of the force, you can figure out the magnitude of the force using the equation at the bottom. Now, generically, if you have equation for a force, it's always due to some object, something created it. I'll call that thing Q1 in this case. And it's being felt by a second object, which the charge of it I'll call Q2. So if Q1 is creating a force on Q2, you multiply the charge of 2, the thing that feels the force, by the electric field of 1, the thing that is causing the force. Okay? So make sure it actually matters which one you have in there. Now, the other thing is that this equation I've left on these vectors on the top, these arrows on the top. And the reason why is that and by the way, the slightly different formatting on these two different characters for the arrow, that doesn't matter. I'm not trying to indicate anything by the different types of arrows. That's just a formatting thing that is automatically created. So what I'm doing is I'm trying to indicate that both the magnitude and the direction. If I just want to use magnitude, I can get rid of the arrow here, get rid of the arrow there, and take the absolute value of the charge. It's equivalent of taking the magnitude of both sides, or taking the absolute value of both sides. And if I want to find the direction, note that whenever you multiply any type of vector, in this case electric field, by a negative number, it points in the opposite direction. So if you have a negative charge that is feeling a force, like in this case, if the electric field is in the one direction, the force is going to be in the opposite direction. So because sometimes they're in the same direction and sometimes the opposite direction, it's very important that you keep clear in your mind what is a force and what is a field, and how there are different things. Force is the response. Electric field is the message created by a charge that will create a force.